Good afternoon, class. We're going to pick up with chemical equilibrium where we left off last time with example 12. So silver 1 carbonate with a chemical formula shown here has a KSP of 8.1 times 10 to the negative 12 and partially dissolves in aqueous solution that has an ionic strength of mu equals 0.005. So the oxidation state of silver is given in the name, but you could also figure out the oxidation state of silver from the counter-ion carbonate from its Lewis structure. It has an overall 2- charge, and we have 2 silver ions for every 1 carbonate, so each silver must be a +1. This is going to be really important for us for figuring out our activity coefficients gamma. So first, we're going to write the KSP expression for the dissolution of silver carbonate with activity, and that's shown here. KSP is equal to the concentration of silver squared times its gamma squared multiplied by the product of the carbonate concentration and its activity coefficient. So determine the molar solubility of silver carbonate with activity. First, we're looking at an ionic strength of mu is equal to 0.005. So again, the table of gamma values, activity coefficients, is organized by charge, so we need to know that silver is a +1 oxidation state. It's a transition metal, so it can have more than one option. So knowing that it's +1 gets us to the right form of silver, which gives us to the correct gamma, which is 0.924. Carbonate has a gamma of 0.742. So when we bring all this into the expression for KSP, we have 8.1 times 10 to the negative 12 is equal to the quantity 2x squared times the square of silver. Remember, there are 2 equivalents of silver, so we have 2x and we have that value squared. Multiplied by x times 0.742 for carbonate. That gives us a KSP that's equal to 4x cubed times 0.634. Divide each side by 0.634, we get 1.28 times 10 to the negative 11, which is equal to 4 times x cubed. Divided by 4, we get 3.19 times 10 to the negative 12 is equal to x cubed. We take the cube root of that to be equal to x. It was asked in class today what the units were for molar solubility. I believe that they are indeed molarity, but I keep molar solubility as unitless generally until I'm actually solving for a molarity. So for example, if we were trying to solve for what the concentration of carbonate was, we would take this value and it would actually be equal to the concentration of carbonate. But if we were to figure out what the concentration of silver was at equilibrium, we'd have to multiply it by 2 because there are 2 equivalents. Now, moving on, we're going to briefly explain why molar solubility of silver carbonate is greater in a solution of high ionic strength. In a high ionic strength environment, silver and carbonate cannot easily recombine to precipitate. So if something can't precipitate, it stays in solution. So lack of precipitation has a flip side of being an increase of solubility. Now we're going to move on to our next example where we're going to calculate an ionic strength with a bunch of ions. So in this situation, we have 0.03 molar of ammonium chloride and 0.02 molar of magnesium nitrate dissolved completely. When it says dissolved completely, we have an irreversible reaction arrow. So we can see that when we are dissolving completely, we have a 1:1:1 molar ratio of our different components. So NH4Cl breaks apart to form 1 equivalent of NH4 plus and 1 equivalent of Cl minus. So each of these 2 components ends up having the same concentration as the original 0.030. However, when we look at magnesium nitrate dissociates to form 1 equivalent of magnesium and 2 equivalents of nitrate. So if we start with 0.020 molar, that is the concentration of our magnesium ion solution, but we have twice the amount of nitrate in solution. Now we need to calculate our mu, our ionic strength, and so we bring all of these values in to our equation for mu. NH4 plus is going to have a concentration of 0.030 times its charge plus 1 squared. Chloride, similar, 0.030 molar, but -1 squared. Magnesium is 0.020, has a positive 2 charge, which is squared. And nitrate is 0.040 molar, it's -1 charge that gets squared. Magnesium we know is going to be a 2+ ion because it is a group 2 metal, but also we know that we could figure out that the charge on nitrate is -1 from its Lewis structure. Inside the brackets, we can calculate to being equal to 0.18. Half of that is going to be a mu of 0.09, which we round up to being an ionic strength of 0.1. And that actually brings us to the end of our unit on chemical equilibrium and will be the end of the material that is going to be on the next exam. We begin our next unit on acid-base chemistry with a few definitions. The Bronsted-Lowry definition of an acid is something that donates a proton. So an overall reversible reaction that we would see for an acid is HA, aqueous, dissolving in water liquid, is in equilibrium with A- and hydronium H3O+. So in this situation, the solvent is actually participating in the reaction. So we have HA is donating a proton and acting as an acid, while water is accepting a proton and acting as a base. So we're going to break down the reaction to its elementary steps. Our first step is HA dissociates to form a conjugate base A- and a proton H+. This is a very slow step and illustrates our proton donor step. Then we have a very fast step. We have H+ protonating water. This entire reaction is in an aqueous environment, so there is plenty and plenty of water around. The moment that H+ forms, it is immediately grabbed by water to form hydronium. In a situation with a strong acid, like HCl, hydrochloric acid, we can see that that dissolves in water and reacts with water to form an aqueous solution of chloride and hydronium. This is not considered a reversible reaction for strong acids, and so we get a forward-only reaction arrow. 100% of the protons dissociate. That means that our concentration of our acid in the reactant is going to be equal to the concentration of hydronium in the product. So here we write that the concentration of HA equals the concentration of H3O+ as a product, as these are in a 1-to-1 molar ratio. In the situation of a weak acid, that is not true. So here, a weak acid like ethanol reacts with water to form, ethanoate, the conjugate base of ethanol, and hydronium, the acid. This is a reversible reaction, so we get an equilibrium arrow here, and not all of the protons dissociate. So this is a less than 100% proton dissociation. So our HA, our acid in our reactant, is not going to be equal to the concentration of our product. So it's not as simple as saying that it is in a 1-to-1 ratio, therefore it has to be the same. We can know this, but we actually need activity, or rather an acid equilibrium, in order to determine what our proton concentration is, and that comes later. But in the meantime, we can say simply that HA is not equal to H3O+ in the products. Our overall reaction, seen up here, HA reacts with water to form A- and H3O+. We can write an equilibrium expression for that. Normally we would write KEQ, but given that is an acid equilibrium, we now write our Ka, A for acid. That's going to be equal to, again, our products over reactants, but this time it's H3O+ multiplied by the concentration of the conjugate base A- divided by our acid HA. Now we can move on and give a similar set of definitions, but from the point of view of what a base is. And a base is defined as a proton acceptor. This is something that grabs onto protons. So in this situation, we have B for our generic base, reacts with water to form Hb+ and OH-. So the hydrogen, one of the hydrogens gets ripped off of water as a proton, so the amount of hydrogen in the base goes up by 1, so we gain a proton and we gain a charge, plus. So it's a nice way of checking to make sure that you've correctly protonated a base. In this situation, our water first must dissociate to form OH- and H+. I consider this a sort of fast step, but it's in quotes because we really have a very large concentration of water, given that it's our solvent, so we always have some amount of OH- and H+ present. When we have some present, the base comes along, grabs the proton to form Hb+. Let's look at an example of a strong base, like sodium hydroxide. That's going to react with water to make sodium ion, hydroxide ion, and more water. In this situation, we have water in the reactant and water in the product, but they're actually different waters. So what ends up happening is you have the hydroxide deprotonates one of the waters, and that pink hydrogen goes on to the brown hydroxide from NaOH to form one equivalent of the waters, and we form OH- from the deprotonated water. So this hydroxide comes from this water, and the protonated hydroxide from sodium hydroxide becomes this water all the way over to the right, which is why I'm including it on both sides of the reaction. Strong bases, like strong acids, are not considered reversible, so we have a single direction arrow. 100% of the base is protonated. This means that, once again, for a strong component, like our strong base, the concentration of B, our base in the reactant, is going to end up being the same as our hydroxide in our product. However, for a weak base like ammonia, that is not going to be the case. So we have NH3 reacts with water in equilibrium with NH4 plus and OH minus. Again, this is acting as a proton acceptor, so NH3 should gain a hydrogen and a plus charge, which it does in the product. It has one more hydrogen and it has a charge that has gone up by 1. Weak base reactions are reversible and less than 100% of the base is protonated. Since it is not a complete dissociation, it is not a complete reaction, we can't say that the reactant B base is equal to our hydroxide product. We would have to calculate this using an equilibrium constant. Our equilibrium constant for a base reaction is written down here as a Kb, and that's going to be equal to our product's Hb plus times OH minus divided by the concentration of our base B. Now, how do we measure the acidity of a solution? The acidity of a solution is measured using what's called a pH. The lower the pH of a solution, the higher the acidity. And the pH of a solution can be calculated from the concentration of hydronium in solution. So let's see how that works. On the left here, I added in a quick little chart showing you a relative pH scale. A pH of 0 to 7 is considered acidic, 7 is neutral, and between 7 and 14 is considered basic. So here we have an example where we have 2.5 moles of acetic acid dissolved in 1 liter of water, so that's going to end up being 2.5 molar since we have 1 liter of solution. At equilibrium, the vessel contains 6.7 times 10 to the negative 3 moles of acetate and the same amount of hydronium. And we have the reversible reaction shown here, and it is reversible because it is a weak acid. So what is the pH of the solution? We don't need an ice table here because we are given values at equilibrium. So our concentration of hydronium is 6.7 times 10 to the negative third moles divided by 1 liter is molarity. So we calculate the pH using this equation. Our pH is the negative log of our hydronium concentration. A few times in this unit, you're going to see this P. pH, pOH, pKa, pKb, etc. This is just considered the negative log of. So a pH is the negative log of the acid concentration, which is hydronium. So we're going to take the negative log of 6.7 times 10 to the negative 3, and that gives us a pH of 2.2. The pH scale is logarithmic, so when we compare our solution that's a pH of 2.2 to a hypothetical solution that's 3.2, the pH of 2.2 is 10 times more acidic than a pH of 3.2. So here, that is how we were able to calculate our pH. Now, let's calculate an equilibrium constant using a known pH. So, in this example, we're looking at hydrofluoric acid. We have 0.41 moles in 125 milliliters of water. The pH of the solution is 1.47 rather. So here's the reversible reaction. Hydrofluoric acid reacts with water to make fluoride and hydronium. Our Ka for this expression is going to be equal to our concentration of our products divided by the concentration of our reactants. We need our fluoride and hydronium. What we have, once we do a little bit of math, is our hydrofluoric acid concentration. So our first step is to figure out what our HF concentration is. That is given to us in the problem. We have moles, we have liters, so we can take 0.41 moles of HF divided by the 0.125 liters of solution, and we determine that our hydrofluoric acid concentration is 3.3 molar. Our hydronium concentration is determined by 10 to the negative pH. Our pH is 1.47, so we can take 10 to the negative 1.47, and that's going to be 3.39 times 10 to the negative 2 molar. From a 1-to-1 molar ratio of our products, now that we know our hydronium concentration, we actually also know our fluoride concentration. So fluoride concentration is equal to hydronium, which is equal to 3.39 times 10 to the negative 2. We now have all of our components to solve for Ka. So we plug in those values and we calculate that Ka is equal to 3.5 times 10 to the negative 4. To summarize down at the bottom, we can go from hydronium to pH by taking the negative log of hydronium to get to pH, And we can go from pH to hydronium by doing 10 to the negative pH is equal to the hydronium concentration.